Okay, this is about the twin paradox, and it's about the real situation where one could be using constant acceleration to get up to high speeds and then decelerating back to nothing, where one would end up having travelled a long way, because one's clock would be travelling slower according to the other frame. But anyway, so just to prove that this one works, let me just choose any old b value. That will be the maximum velocity that one, at which point one is going to start decelerating by turning the ship around. It's described here on the internet. I'm going to use the relativistic starship calculator, and so I'm just randomly set a maximum speed of 0.888, and that would mean that one will get 2.14 light years. And so how much time will it take? Well, if one's using a constant acceleration of 9.8, which is the same as Earth, then one's going to feel 1g the whole time, and it's going to take Bob 2.669 years, and it's going to, and 3.59 years is going to pass for Alice. So let's see if it's correct. So first of all, I better put in the distance theoretically that one is going to get, which is 2.1445 say, and one is going to travel at acceleration of 9.8 for the whole journey. So now we can calculate that, and if we look at the value, we see time on Earth is going to be 3.59. That's the proper time for Alice, and the proper time for Bob is going to be 2.66. So that works out, and here's the 0.88. You can see the maximum speed he's going to get to when he turns around, and you can see the kinetic energy. Okay, so the calculator works. Just better give another example. I'll give an example from here. Let's say you want to get to the spiral galaxy M101. It says it's 25 million light years away. Okay, so let's put that in. 25 million light years, and you want to travel at a comfortable 1g. Calculate it. Okay, it should take 33 years for Bob, and it should take 25 million years for Alice. So I already know what to put in here. It's going to be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 7, and Desmos can't handle that, so you have to make that a 10 so that it can. And of course, notice that the R value is irrelevant. So here we are, 25 million light years, and for Alice it's going to take 25 million years, but for Bob it's only going to take 33 years. And what's the difference? There's a lot of time dilation. You can see for every 1 second that passes for her, only 0.000013 seconds passes for Bob. Kinetic energy, yep, you can see that's right. Okay, so it works. Let's say one more. Let's say you want to get to Alpha Centauri, which is about 4.2 light years away. That's 4.2, travelling at 9.8 acceleration the whole way. Calculate that. Here we go. Oops. Time on board according to Bob, 5.32, that's right. And according to Alice, 5.82 years will pass. So his clock is running at 0.6 for every second of her time. Only 0.6 of a second is passing on average, because we have to use the natural log, because it's going to accumulate all this redshifts. You see, that's all that's happening. I'm just using the redshift and I'm just accumulating it using the integral natural log, putting it over proper velocity. Oh, it's just the frequency, Alice's frequency. Anyway.